Good morning, everyone. Thanks for coming in this beautiful sunny day. All right, so first let me ask if there are any questions. Well, we had a question session and we'll have another one, so if you have something to ask, you can also do it then. All right, I don't see anything, so let's continue with this 3D n equals to 2 critical OS Zumino model, which we claimed yesterday, or I claimed, is the infrared fixed point of this classical Lagrangian theory that we were writing down. And so once you know this, there's this useful tool which I told you a little bit about, the conformal bootstrap, or rather the modern incarnation of this idea, which is to study, for instance, 4-point functions. Study the 4-point functions. So the simplest one that you can imagine, I have one field in the classical theory, phi. It is a superfield, but I will explain what I mean. So you study the 4-point function. One thing that you should make sure is that the U1 charge, the U1R symmetry is actually conserved. So you know you have to do these conjugations. So this has R charge 2/3. This has minus 2/3, 2/3, minus 2/3. So the total correlator has R charge 0, which means that it is allowed. It can be non-zero, right? Because otherwise, if I put only the phi's here, it will vanish by this U1R symmetry selection rule. All right, so you study this, and this is actually not one 4-point function. This is a system of 4-point functions, because at the conformal fixed point, the expectation is so that this is a chiral superfield, and at the IR fixed point, this field will be, well, field is a classical concept, so it will be an operator in the quantum theory, and operators should fit in the superconformal multiplets. And so phi and phi dagger should be in these multiplets of dimensions 2/3, 0, 2/3, and then its friend. I'm not sure I'm consistent with the signs, but so this is the expectation. And these multiplets contained, you know, a superconformal primary, which is a scalar, and then a fermionic descendant, and then another scalar. So actually, this is a system of multiple correlators. So, but the logic is exactly the same. You use the operator product expansion to fuse, if you wish, 2 by 2 these fields and write down an expansion in what's called conformal blocks. But now you have essentially a vector of conformal blocks, and you can combine it into one big object. It's called a superconformal block. But this, again, kinematical constraints, meaning it's imposed entirely by the symmetry of the problem. So I have the conformal symmetry, but I also have these fermionic generators, the SUSY generators. And so combining all of that, I can expand these 4-point functions into what's called superconformal blocks. I'm not going to give you the details, but the logic is exactly the same. And then you ask, what are the constraints? You know, you try to numerically solve this equation, which you cannot solve because it's infinitely many equations, infinitely many unknowns. So the idea is to try to exclude, to try to show that some choices of these conformal dimensions, and OP coefficients are not allowed. Some of you, as I heard yesterday, have been working on this, so for them, this will be boring. But just to give you a sketch what we know about this CFT, if it exists. But okay, I think it exists, so let's study it. So when you study the OP of phi and phi bar, or dagger, I'll be using bars actually today. Why not? So I will use somewhat strange notation. So we have a strongly coupled quantum field theory. So the operator phi squared, or phi bar, is not simply the product of the fields, right? These are composite operators, and in a non-trivial QFT, their conformal dimensions are not related to the conformal dimensions of the operator phi. So for every composite operator, every product of the fields, you have to compute independently the conformal dimension. So what I know here is that these fields have opposite R charge. So this OP has, so on the left-hand side, so this is the OP. I'm schematically writing the product of these two operators as an infinite sum of other operators in the theory. So here, each of these things is a local operator which must have R charge 0. But otherwise, we don't know much about these operators, except the first one. The first one is a simple one, identity. And then there's an infinite expansion in conformal primary operators, which I call like that. So I order them by the dimension. So this is the lowest non-trivial. So this one has obviously dimension 0. This one will be the lowest non-trivial operator, the lowest conformal dimension above 0. And then this one is the next one, and so on. So there is one assumption here. I'm assuming that the spectrum of conformal dimensions is discrete. Strictly speaking, this is an assumption, but in more than 2 dimensions, I'm not aware of examples that violate it. So we will assume it. So you're imagining a discrete collection of real numbers here. And so one question is, what are the allowed values of the dimension of this operator? And so this type of question is what the modern bootstrappers can say a lot about. So you could ask, using some fancy code, numerical code that some of you, at least one of you, I heard yesterday, was having fun with. Someone was working with Alessandro Vicchi, so yeah, they know all about this. So you essentially pick a point here. So this is some random choice of numbers for these two quantities. And then you ask, for this point, can I solve this equation? It sounds a little bit like a crazy question to ask, but the structure of this equation, which I'm not explaining here, allows you actually to answer that question within some accuracy, right? Like every question that you ask a computer, there's some, uncertainty. And so you ask this question many, many, many times, and then you make an exclusion plot. So, and roughly speaking, in this example, it looks like this. So there's this. So everything above here is not allowed. So this is excluded because the data points here cannot obey this equation, assuming unitarity. So I'm assuming that the OP coefficients are real and that the dimensions are, obeying all these bounds that we talked about. So everything above is not allowed, and everything below is allowed. So this, I'm not going to call a CFT. It's just that with this method and with this analysis, I cannot exclude these points. Okay? So strictly speaking, this is what the computer spits out, if you ask it kindly and in the right way. Then when you see a plot like this, well, you immediately ask, you should ask, your smart kids, you should ask what happens here. Why is there this feature there? What, I mean, otherwise these are some smooth curves here, okay, but what happens here? And where is the location of this point? And then what we found in this context, in this specific example with n equals to supersymmetry, is that this value is at delta phi approximately this number within some accuracy. Okay? So then at this point, you check your expectations, right? Based on this, whatever, argumentation without a calculation, following Strassler's approach, you would expect if this CFT is actually there, that it will have this operator exactly phi to have a conformal dimension 2/3. Well, that number is pretty close, right? This operator, however, is not what's called a protected operator. These are not short multiplets, I should have emphasized. Not short, which means that they're long. So their conformal dimensions are not fixed by their R charge, which is a good thing because their R charge is equal to 0, and the conformal dimension cannot be 0, except for this guy. Okay? So delta phi bar is a mystery of science, right? So we don't know how to compute this. Well, you can use the 4 minus epsilon expansion, but we don't know how to compute it exactly, analytically. Well, this curve suggests, well, by the way, this value is a little bit smaller than 2. It's some number. Something like this. So you just read off the value at this kink. And you optimistically declare that that's your answer for this quantity. Okay, so that's roughly what the modern bootstrappers do from time to time. They search for kinks like that, and then optimistically declare that at the kink there is an actually interesting CFT living there. So, you know, the exercise is to identify what is the CFT. We don't have a proof of this principle. We can only kind of have evidence for it. There's more sophisticated analysis that instead of such an exclusion plot with 2 regions, people actually make an island around this. This island is not like the islands that solve the information paradox, or the islands that you go to the beach to. These are different islands yet. Anyway, so you can push this and analyze this further, but the basic idea is that the claim is that here there's a non-trivial CFT, and simply by looking at the dimension of this guy, you are entitled or kind of encouraged to identify it with the 3D n equals to 2 critical Wessel-Minor model. Okay, so then sitting at this point, actually it's not obvious from the plot, but from the numerical analysis of this equation, you can start extracting numerically the conformal dimensions of other operators. You're not supposed to understand this in detail. I just want to give you a flavor. So, for instance, for the low-lying operators, we were able to kind of extract these numbers. Okay? This operation has some limitations. The further you go down this list, lose accuracy, and at some point you really have to stop, because you really cannot analyze infinite dimensional equations on a computer, so you cut off this kind of what's called crossing symmetry equations, and that limits your numerical accuracy. So in practice, in the real world, you can only go up to whatever, the first handful of operators, 5 or 6 or 8 operators. Yeah. Any questions about this? Yes? Well, yeah. Right. You can, yes. Indeed, in radial quantization, you can say it looks like I'm quantizing something on a sphere, so it should have a discrete spin. Right. I haven't thought carefully about loopholes in this argument, but as I said, I don't know of an exception. In 2 dimensions, the sphere is a circle, so you can maybe evade this because the circle has a 0 curvature. And in fact, in 2D, we have examples. Leuven theory is an example of a theory that is a CFT, but has a continuous spectrum. So anyway, I don't want to go into this, but any normal QFT will have a discrete spectrum in this context. Right.
I have a question.
Yes.
So in 2 dimensions, we usually only take the singular part of the OPE. Why are we not doing that here?
Right. So yeah, good. So I haven't really talked about, this is a schematic equation. I'm not claiming that this is regular as an OP. I'm just giving you the operators that will appear. So singular or regular will be determined by the position dependence of these fields, of these operators. So this will be a singular OP in that sense.
Oh, I see. Okay.
Right. So I'm being schematic here, just to kind of introduce labels for these operators. All right. So this you can call all of this a numerical approximation scheme, a non-perturbative, but still approximate by this numerical analysis approximation scheme to solve, big quotes, this non-trivial CFT. Okay. The big quotes is that, I mean, every time you hear someone solving a QFT that is not a free theory, you should know that they're lying to you, right? So that's really true, because usually they mean something specific. They're solving for some observables. So for instance, here there's non-trivial line operators that I have nothing to say about. No idea. Some of you are working with Carlo Menengeli, as we heard, so he has probably some ideas how to say something about line operators. But anyway, certainly not all of them. Okay, so now I want to emphasize another observable, which I briefly mentioned. So this is the 2-point function of the energy momentum tensor. So this exists in every CFT, and in some sense this quantity informs you how much energy you have in your system. There is some normalization there that is chosen kind of randomly. Okay, so you have this quantity, and I still have to tell you what the p's are. I'll do so in a moment. Okay, so the p's are some tensors that basically have the correct index structure, the correct symmetries, and their job in life is to produce a conformally covariant expression. So this is the part that is fixed entirely by the kinematics of the theory. So as I told you, so for a two-point function of a scalar, it was very simple, right? Just to remind you, this is all, right? So you have an operator at point O, an operator O at point X, and an operator O at point 0. It's the same operator, the dimension is equal to delta, and then the two-point function is just 1 over the distance to the power 2 delta. For operators with spin, this structure is more complicated, but completely known. It fits on one line, 1.5 lines. So the interesting information here, by the way, the power of X here is fixed because the dimension of the energy momentum tensor, it's a conserved current. So the dimension of T is equal to 3. In general, it's equal to the dimension of space-time. Okay? So the only thing that we don't know in this two-point function is the coefficient. If you are not fully asleep, you can wonder, why was I able here to put a coefficient 1, whereas here it seems like this is a non-trivial number? Roughly speaking, it's because the energy momentum tensor is a composite operator. So if you write down a scalar field theory, it's built out of derivatives of the scalar, right? And so you can normalize the scalar two-point function to be 1, but once you do that, any composite operator will have a new dynamical coefficient, which we call here CT. So CT is a meaningful physical observable. So in some instances, this is even an experimentally observable thing. This knows about heat transfer in some critical system and so on. So this is really a physical thing. All right, so using this machinery that I haven't told you too much about, one can extract this an approximate value for this quantity. Okay, so this value, very soon I will explain to you how to compute it with how to compute it analytically with other means. So at the moment, this is some numerical approximation that comes from just zooming in at this point and blindly believing that this is n equals to 2 CFT. Okay, so that's basically what I wanted to say about this bootstrap approach. I mean, there's much more to say. One can teach a whole course on it, but I'm not going to do that. Any questions? Right, so the question for those of you online was why this non-trivial interesting CFT seems to lie on the boundary between the two regions. So first of all, the boundary of these two regions is an approximation. So you start excluding, and as you increase numerical accuracy, there's actually a series of curves like that. So if you do a very crude approximation, if you keep in this infinite expansion of the crossing equation, if you keep only, let's say, 2 terms, You'll find a very rough bound that is far away. Then as you keep on including more terms, it gets better, better, and better, and then you seem to converge. So this is like, looks very, very accurate. When you keep 20 terms, 21 terms, and so on, you don't get much improvement, and at some point, you have to stop. So we don't even know any analytic properties of this curve. So that's the first thing to emphasize. And then why non-trivial CFTs lie not only on the boundary, but on such kinks is, I don't think it's understood. So it's a little bit of a black magic. It is not true that all CFTs that we know of can be identified with such kinks on such curves. This is not true as far as I know. So you have to be a little bit lucky. So in some sense, there's the simplest CFT with a given symmetry. For instance, this is the simplest model with 3D n equals to 2 supersymmetry, no flavor symmetry, as we said. So this is really the minimal thing, and somehow the minimal things lie on such kinks. But this is an empirical fact that I don't have an explanation for. Maybe there is an explanation. I've worked on this just as a hobby, but I'm not really an expert. There's people who know much more than me, but I think it's not understood, is the short answer. So, by the way, this method, when applied to the 3D easing model, lambda phi to the fourth, to the CFT, arising from that theory, apparently leads to the most accurate estimation of the critical exponents. So it beats Monte Carlo and so on. Beats every other method that we know of. So we can find the dimension to, I think, accuracy of 7 or 8 digits after the comma. All right, any other questions? All right, good. I want to, so memorize this number, okay? We'll see it kind of emerging later on. Maybe in the afternoon. Okay, I want to emphasize that I've told you a story about this simplest model I can think of that is non-trivial and has n equals to 2 supersymmetry. But there's actually a large class of 3D n equals to 2 with Zumino models. So you can now, well, a certain class of them you can understand in this simple way. So I take n chiral superfields with a canonical scalar potential, and I take the superpotential to be cubic. Okay, so these couplings, Hi, J, K, they specify the details of my interactions. So I have a lot of freedom here in choosing them. So so what I'm specifying here is the classical Lagrangian of the theory. You can do the same analysis as before and show that this is an asymptotically free theory. So H will be free, and these will be relevant operators. So they will drive an RG flow, and then in favorable circumstances, well, I think almost always, you'll end up in some CFT at low energies. So there's a large zoo of such models. Yeah, something that I forgot to say is that this number over there in the box, 19098, you can do the 4 minus epsilon expansion to 4 loops, and you get within 0.1% of this number. If you do this illegal operation of doing epsilon expansion and putting epsilon equal to 1. So that's another kind of highly non-trivial evidence that that this thing at the kink is actually that CFT. So, I mean, this is a whole zoo, and one can go nuts and study it. I just want to point to an interesting example. So, one example that we kind of already talked about a little bit. So, take 3 chiral superfields. So, there is a curly n, which is the number of supercharges, and there's a flat n, which is the numbers of fields. Yeah, such is life. So I choose this cubic interaction. Why do I choose this? Well, I'm a free man. I can choose whatever I want. Okay, but this one we already saw. Like, if you put H2 to 0, this is your friend, or our friend, the XYZ model, except that its X, Y, and Z are now called phi 1, phi 2, and phi 3. Right? This is the model that I gave you an example of in the context of the moduli spaces. There was these 3 cones, blah, blah, blah. And I told you that at the origin, there's a CFT. And that's the CFT. That this, yeah, I stay by my words that there's a CFT. All right. If H1 is equal to 0, well, this is like 3 independent copies of the Wess-Masumino model that we studied before. So 3 times the critical Wess-Masumino model. They really don't interact with each other, so these are decoupled copies. Then, of course, these are 2 limits of the general case. So the ratio, so only the ratio of the couplings is actually non-trivial, because you can rescale all of the fields by the same number and get rid of one of H1 or H2. So if both of them are non-zero, only the ratio is meaningful. This is a complex number that is a ratio of 2 non-zero numbers, so it parameterizes a space. It's a variety. For those of you who know what a variety is, it's a space. That's what a variety is. My goodness. So any idea what this variety is? If you have a PhD, you're not allowed to answer this question. If you don't have a PhD, you are encouraged to answer it. No? No one? Correct, it's a solution of algebraic, but I claim it's a smooth manifold. Yeah, so you can view it. So it's simply the complex projective space, CP1. If you don't know what CP1 is, well, it's just S2. If this is not obvious, Wikipedia will answer your questions. You have a ratio of 2 complex lines, and that gives you a 1-dimensional complex space, and you exclude zeros, so it's a sphere. Okay, so we learn that there's that I have a parameter here in my superpotential, which has geometrically lives on S2. So for every point on S2, I have a Lagrangian, is my point. Now, the magical fact is that this ratio of the couplings doesn't get renormalized along the G-flow. This is not obvious. You have to study beta functions and so on. So you actually have to do a calculation, which I'm not going to do. But the claim is, I mean, it's not so hard, but actually it's in the Strassler review. He has half a page on this fact, so you can look it up. But what happens is that you undergo an RG flow, and for every value of tau, you have a different CFT. Right? So you can choose H1 and H2, undergo this RG flow, have a CFT, change H1 and H2, undergo it again, and have a CFT, and so on. These CFTs, so tau parameterizes a conformal manifold. Okay? So they're not the same CFT. The spectrum of operator of dimensions is going to change, but in some sense, in the RG sense, they lie at the same height, RG height, so to say. For instance, the two-point function of the energy momentum tensor is the same as you vary tau. So the amount of energy that you have in the system is the same. So if you think of some analogy with quantum mechanics, this is a space of ground states that has the same energy. Okay? So this is a non-trivial fact, and if you slightly vary the choice of Hij, this thing will not happen. So for instance, if you add, if you add phi1 square, phi2 as another term in this action, this thing will be gone. So the RG flow is going to change. There will be a CFT, but it will be at another point, and it will be isolated. It will be a point. Anyway, so the fact, what happens, so you have, that's how a sphere should look like, and tau is a complex coordinate on the sphere. And so as you vary this as you vary the point on the sphere, you change the CFT, and roughly speaking, in one parametrization of coordinates, this is the North Pole and this is the South Pole. So this will be whatever. This will be XYZ, and this will be 3 copies critical as the Zumino model. And then everything in between will be some other CFT. So what you can ask, what happens to the spectrum of operators as I vary tau? So I have infinitely many CFTs, and I can ask that question. And you can show that semi-short multiplets, and also the short one, semi and the short one, have dimensions that are independent of tau. So the spectrum of those operators is the same on this sphere, which is why sometimes operators like this are called protected operators. So meaning that you have a coupling tau, and as you vary the coupling, the dimensions don't change, so something protects them. What is that something? Supersymmetry. But you also have the long multiplets, like our friend there, phi phi bar. So long multiplets or unprotected operators. Depend on tau. Okay. So I want to give you one example of this because we did something with my friends. So the simplest a long multiplet or a long operator that I can construct, unprotected operator, is this one. So I take the complex scalar fields out of each of these chiral superfields, and its conjugate, I multiply them, and then I sum over I. And so you can do a for loop 4 minus epsilon expansion, because why not? It's fun. There's so many Feynman diagrams. And you find this answer that probably I should not be writing early in the morning, but you know, I will. So those of you who have done more than one loop in their lives will recognize transcendental numbers appearing. This is not an accident. They always appear when you do loops. And this whole thing multiplies epsilon cubed. And then there's a big nasty animal that is the for loop guy. But I'm going to stop at 4 loops. I think one can do also 5 loops. And there's a person who looked at that, but yeah. Final term, 20, it's 20, zeta 5. So one comment is that as you increase the number of loops, you get coefficients with increasing transcendentality. If you don't know what this means, you're not going to learn it here, but it's essentially the order of the zeta functions that you get. So at 3 loops, you get zeta 3. At 4 loops, you get zeta 4 and 5. So yeah, you have some structure like that, which you see actually in usual Feynman diagrams also. I mean, in other contexts. Okay, so this explicitly shows you that as you move along the sphere, along this tau, the dimension of this operator changes non-trivially. There's some accidents at 1 and 2 loops that hide this from you, because this operator enjoys some special discrete symmetries, but you know, this is special for this one. If I study some other one already at 1 loop, I'll have a non-trivial dependence on tau. And then you'll see some complicated non-holomorphic functions controlling how this operator varies. The dimension of this operator varies on the sphere. Okay. One thing I should inform you is that this thing that I said about the short and the long multiplets actually is a little bit of a lie, but as usual is morally true. So it could happen that there is a spectrum rearrangement. It could happen that as you vary this parameter tau, 2 short multiplets, semi-short or short, their energies, their dimensions conspire such that they can form a long multiplet. Right? The long multiplets with this amount of supersymmetry have 16 states, and then so you have to carefully look at the table that I was drawing and find which short multiplets can recombine into a long one. And there's a finite list, and this list has been written in this big paper I told you about of Cordova, Dumitrescu, and Intelligator. And so you could ask, does this happen here? Does this accident happen? It can happen only for a finite number of multiplets, and it does happen. The reason it happens is that for certain points on the sphere, you have enhancement of symmetry. So, for instance, just to be a little bit precise, if H2 is equal to 0, so this model has, sorry, I should write it here, has U1R symmetry where every field gets, so the R charge of the operator phi I is 2/3. Right? Giving charge 2/3 to each of the fields, make W has R charge 2, which was our convention for the normalization of the R charge of the superpotential. When H2 is equal to 0, I have an independent U1 flavor symmetry, which gives the following charges: 1, -1, and 0. I can choose also 0, 1, -1. So there's obviously permutation symmetry. So this choice of charge assignment is a flavor symmetry, I claim, because it gives the superpotential charge 0. And it's also an orthogonal vector. It's an independent, so maybe I should be more pedagogical. So there's fields. There's U1R, and there's U1 flavor. 2/3, 2/3, 2/3, and 1, -1, 0. So this vector of charges is orthogonal to this one. When I multiply them, I get 0. And this one gives charge 0 to the superpotential, so it's an independent flavor symmetry. And obviously, this one will be broken. So it's only there when H2 is equal to 0. Because if I add a cubic term like this gets charge 3, and this gets charge -3, so that's inconsistent. Okay, so at the North Pole, in my conventions, I have an enhancement of symmetry, so I have to, for instance, the multiplets should suddenly rearrange such that I have a flavor symmetry multiplet, one of the short multiplets. And in fact, they do. But these are special situations. On a generic, if you vary somewhere here, nothing like a rearrangement will happen, and what I said is true. So it's only at special points that these rearrangements can happen. Final comment. This XYZ model, this model with H2 equal to 0, has an interesting property, or it illustrates another deep idea in quantum field theory that was emphasized by Seiberg. Well, I don't know how to call this. Dualities. So this is not in my notes, so I will improvise a little bit. But basically, you have UV, and there is the Lagrangian of XYZ, which is specified by the superpotential above. And then there's another Lagrangian, which is U1 quantum U1 gauge theory, so quantum electrodynamics, with n equals 2 supersymmetry. So you have the gauge field, and you have a certain fermion also, which is a superpartner from the gaugino. And then you add one chiral multiplet in the fundamental representation of the gauge group. So one chiral. So that's your UV Lagrangian. And so when you look at these models, they have seemingly nothing to do with each other, right? If you look at the Lagrangians of these models, and if I told you that they're the same, that they have exactly the same physics, you would think I'm crazy. Well, you should. But the deep fact is that they do. So they flow in the IR, they flow to the same 3D n equals to 2 CFT. Yeah. So if you're not impressed by this, you should really sit down and think about it. It's hugely an impressive fact of life, and yeah, it's true also. And this is just a very, very, very simple example of such interplay, meaning two UV theories that have very, very different Lagrangians and different descriptions and different fields. Like here I have a gauge field, I have you know, a photon here. Here I don't have a photon. But at low energies, these things have exactly the same physics. The same partition function, the same correlators, everything's the same. And yeah, and this happens also in 4D n=1 theories, happens in two-dimensional theories, all over the place. Yeah, I don't want to say anything more about this because also I don't have anything written down. But yeah, if you have any questions about this class of models, now is the time to ask. No? Right, so yeah, so here I'm doing the 4 minus epsilon expansion. So the calculation here is a very Lagrangian calculation. So I'm in 3.99 dimensions, so I have a perturbation theory. And so really, these are the fields in the Lagrangian, okay? So I choose this operator, if you wish, normal ordered. That's my choice. I mean, I have other ones, like, for instance, I have this guy. This is an independent operator from this guy, right? Well, okay, sorry. Now it's independent. They're orthogonal operators in the Lagrangian. Okay? So this O hat is another unprotected operator. And these two operators will have different values of delta, I claim, and they will have different functions controlling their dependence on tau. So which one will be the lowest one will change as I vary tau, actually. So they kind of switch places. Exactly. So because before I had an isolated CFT, I really had a notion of the lowest operator because I have just one point. Here, when you pick a point on that sphere, which combination of phi bar, so you know, in general you have some operators like this. I should not call it H. Okay, so this operator I will call I don't know how to call it, O tilde. So I do a sum over I and J, right? And then I should study which are the orthogonal combinations. I will have 9 of them, I think. So I have 9 independent operators like that. And then when I fix tau, I can use the 4 minus epsilon expansion to compute the dimensions. And one of them will be the lowest, and I will call that phi whatever. O prime. It will be the first one that appears in the OP. But as you change tau, which one will be the lowest will be modified. So actually it's a very rich story because the spectrum depends on tau and things rearrange. The OP depends on tau. Everything depends on tau. It's a non-trivial example, which is why I'm emphasizing it. I'm not sure if I answered, but yeah. Any other questions? All right, so now we change gears completely to the fourth tool that I advertised we have to study these models, or many other models actually, which is called supersymmetric localization. But since anyway, I don't know when I should stop. There was a somewhat offensive comment by one of you yesterday, which I found unacceptable. So I will, off the cuff, make comments about that comment. So one of you, who shall not be named, but he knows who he is, said that he works on the 2,0 theory but doesn't know what the 2,0 theory is. Which is a good thing to work on the theory, and it's a good thing that he doesn't know because no one knows. So that's a fact of life. But we know it should exist. So this has nothing to do with the rest of the class, by the way, so it's some casual comments. But I told you, well, it's related. I told you that superconformal algebras are completely classified. And they exist up to dimension 6. So when you have an upper bound, you should go to the upper bound and see what happens there. So in 6D, you have 2 superconformal algebras. I'm not going to write the notation here, but this is the maximal number of dimensions that you can have a superconformal algebra. And so there's a 1,0 and a 2,0 superconformal algebras. The reason there's a comma is that spinors in 6, so left and right, there's a notion of that, and in 2D also. And so in 2 dimensions and 6 dimensions and also 10 dimensions, when we talk about spinors, you should say what the duality is. So this means that you have, whatever, 1 chiral spinor, left-handed, let's say. So it's always confusing when people, at least when I was a student, I was very confused by these curly ends. So the somehow invariant thing to say is the number of real components of the spinor. So here you have 8 Qs and 8 S's. And there's an algebra involving those. And the R symmetry is SU2. SU2 R symmetry. In this example, this is the maximal number of supercharges you can have. And R symmetry is SO5. Okay? And so this is as much supersymmetry as n equals 4 super Young-Mills in 4 dimensions. Okay, so these are mathematical facts. And the question that so this was known since 1976 or 7. And a physicist should ask, are there quantum field theories that realize these algebras? And if you're a boring quantum field theory person, meaning you're very good, but you only know the Peskin and Schroeder, you will quickly, well, maybe not so quick, but you can start asking this question systematically, and you will conclude maybe that there aren't such things, because Lagrangians written down with gauge fields and spin 0 and spin 1/2 fermions are non-renormalizable in more than 4 dimensions. It's confusing. If you have spins more than 1, I don't know how to quantize, gravity is hard, then you can say, okay, these things are very, very exotic. However, you should not be a boring QFT researcher, you should be a string theorist. And then you should understand, hopefully, string theory, or at least try. And then you learn that string theory is a wrong name, it's not a theory of strings, blah, blah, blah. There's a thing called M theory. And the fundamental degrees of freedom of M theory are M2 branes and M5 branes. So the 2 and the 5 indicate the number of spatial dimensions. So this is a 2 plus 1 dimensional object, and this is a 5 plus 1 dimensional object. Okay? And so you can ask what happens at low energies what is the dynamics of these objects at low energies? Experience with D-branes indicate that there should be some kind of quantum field theory. When it's D-branes, every child knows that open strings can end on D-branes, right? And so these open strings carry here Maxwell fields or Yang-Mills fields. And so if you have a stack of D-branes, you can have these strings also between brane 1 and brane 2. And so these two will give you a U1 Maxwell field, and these two will give you the off-diagonal components. And so if you have coincident branes, you have a non-abelian Yang-Mills theory. In this case, if it's two branes and I put the distance to 0, I have a U2 Yang-Mills theory with some amount of supersymmetry. And then if I pull them apart, the length scale of this string gives me, realizes the Higgs mechanism and breaks this to U1. U1 squared, actually, but anyway. And this extends to every n, like that. Okay, so this is understood. You can read about it in Burczynski's book. But here, I don't have strings. I have m's, M and m's, right? So I don't know what to do. But you can be inspired and try to figure out what happens. Anyway, the claim is that in both of these situations, on the word volume of these M-branes, you have non-trivial conformal field theories strongly interacting. This one we understood in 2008. It's now called the ABJM theory, also known as the Bagger-Gustafsson-Lambert theory. And so this is some kind of a three-dimensional quantum field theory with n equals 8 supersymmetry. So the maximal amount in 3 dimensions, which is exactly these numbers, is called n equals 8. So this is nice and important. And we now have tools to study this in some detail. The claim here is that you have a 6-dimensional n equals to 2, 0 CFT on the word volume of n coincident branes. And so this is what one of you claimed to not know. And the reason this is a mysterious object is that this is really not a gauge theory, right? In this example, it's some Chern-Simons theory. In n equals 4 Yang-Mills, it's Yang-Mills theory. And here, this is somewhat exotic. So one thing that we know happens is that there is a non-trivial tree form in the game. When I have one M5 brane, I can analyze the details here. And there is a tree form that obeys something like this. So there is a self-dual object in the theory, and when it's abelian, when I have one of them, you can study this, expand in Fourier modes, and fool yourself that you understand. But people don't really know how to treat non-abelian n-forms. There's a name for it. It's GERPs. So if you have to study GERPs. These are some animals that I don't know what they are. And so that's one of the reasons we don't understand this. But there's various tools, including the conformal bootstrap, that have been used to kind of access information about this theory. So it's a mysterious beast, but it's an important beast because in some sense, this will be an exaggeration, and if Nikita Nekrasov is watching this video, which of course he won't be, but he will kill me probably about what I say, is that every supersymmetric QFT that we know about can be obtained from this one. So this is a very strong statement, I know, but roughly speaking, it's true. So you can start putting this theory on non-trivial manifolds, like let's say R4 times a Riemann surface, and then go to low energies much lower than the diameter of the Riemann surface, and then you get an effective four-dimensional theory. And then if you do some mumbo-jumbo on the Riemann surface in the correct way, you'll keep a number of supercharges invariant. Not all of them, but some. So, for instance, if you choose here the torus, the flat metric on the torus, this is really a special case, and you keep all the supercharges. So that will give you n equals 4 Yang-Mills, for instance. And then if you start inserting here some defects, punctures, lines, and so on, interesting things can happen in the four-dimensional theory. You can keep on going, and you can do 3 manifolds. And again, you find a whole zoo of three-dimensional SUSY QFTs in this way. For instance, this XYZ model is realized by some exotic choice of a manifold M3. So this very simple XYZ theory that I told you about is a specific instance of this 62,0 theory on a hyperbolic manifold of a special kind. So that's strong motivation to understand what this is. So yeah, I'm not going to say more, but yeah, that was my digression. It's an important beast. In some sense, all of you should be working on it, I think. But maybe not, yeah. Any questions about the 2,0 theory? Okay. Everything's clear about it, good. Now, where was Omar? Is he here? No. He's not even here. Oh my goodness. Yeah, so what I said about all SUSY QFTs obtained by the 2,0 theory, you can easily find counterexamples. So we currently have some QFTs that we don't know how to obtain, but my personal feeling is that this is due to lack of imagination. Ultimately, this will be the way to find all SUSY QFTs, I think. No, I mean QFT, including the massive ones, yes. So, for instance, if you put M5 branes on a sphere without any twist or anything, or even if you do a twist, you can get QCD with a mass gap. Sorry? I intentionally made a provocative statement so that people can wake up. Yes, I know it's very strong. So in the limited situation where we have 40n equals to 2 CFTs or QFTs, which is still a very large class, well, Nopadol knows this much better than me, but essentially, in some sense, almost all of them, or all of them, I don't know exactly the current status, can be obtained from M5 branes on a Riemann surface with sufficiently complicated defects and punctures on the Riemann surface. So that, at least for those SUSY QFTs, this gives you an organizational scheme. But is this roughly true what I'm saying? Okay. All right, so you should erase all this 15 minutes from the recording, or if it's actually true, keep it and then in 25 years, play it out. Somehow, one of these two things. Well, okay. Certainly, it has been this approach of reducing the 2,0 theory. I think that this is a fair statement, has opened up new possibilities for constructing SUSY QFTs that are not based on a Lagrangian. I think that's a fair statement. So there's a huge classes of quantum field theories that we learned about by playing exactly the game I said. So that's a more conservative statement. Let's end with that. Yes. Yeah, if I start speaking about the swampland, this will really be should really be erased. I'm not sure how this is right. So the meaningful version of the swampland program involves quantum gravity, right? So here I'm always decoupling the closed strings degrees of freedom at the moment, or whatever, closed membranes. So I'm decoupling gravity. Yeah, so in that sense, it doesn't have implications at the moment. But you could ask, in a six-dimensional theory of quantum gravity, arising from, well, coupled to the 2,0 theory, which is a quantum field theory, so what will be the constraints of such theories of quantum gravity? And that question is a different one from what I was mentioning. Yeah. So, for instance, there's been recent work by Vafa and collaborators that even for n equals 4 Yang-Mills in 4D, there's nothing wrong with studying the theory with SU 100 gauge group. N equals 100. It's a good number. And the claim in the paper is that if you couple n equals 4 to gravity in 4 dimensions, you cannot crank up the gauge group above a certain number, 27 or something like this. So these constraints are only visible, well, in that context, only visible when you have, dynamical gravity in the story, which we don't have in this course, luckily. All right, so enough general nonsense. And again, if I've made too strong of a statement, it was kind of intentional, right? So the next 2 hours or so, Davide is even going out and what did we do inviting this guy here saying wrong things? All right. So I'll start with something very simple that many of you have seen probably, which is the stationary phase approximation in ordinary calculus, ordinary integrals. And ultimately, we will use this as a model for the path integral. Since we don't understand really the path integral, we start with things that we do understand and then kind of imagine what could be true. Okay, so take a smooth. So this is a smooth Riemannian manifold with metric G and dimension 2 times L. So it's an even dimensional compact smooth manifold. Okay? And I'm studying integrals of this type. Well, you could study integrals of this type. So this is the invariant volume. I integrate over the full manifold. And then I put some somewhat annoying integrand, which is, so this is a real function. And this is a real number. Okay. Why do I study this? Well, because the path integral in quantum field theory looks, or quantum mechanics, looks a lot like that. So, roughly speaking, the map is F is the action and T is 1 over h bar. Right? This is the analogy. Okay, so you could ask in physics, you could be interested in what's called the WKB approximation or the semi-classical approximation where h bar goes to 0. And then, of course, what's going to, we we know that in that limit, the classical configurations dominate, meaning the solutions of the Euler-Lagrange equations are going to dominate. So in mathematics, this is called the stationary phase approximation. So how does this work? As t is very large in this language, this thing oscillates rapidly. And the main contribution will be from the critical points or the fixed points, the stationary points of f. The dominant contribution is from the points where d of some point k vanishes. Okay? So for the moment, assume that these are isolated points, just for the sake of argument. You can do this, of course, for whatever loci of isolated points. It can be made much more precise. And then at those points, the answer for this integral takes the following form. So limit t going to infinity, zft. There's some coefficients. You have to sum over all the critical points or the fixed points. There's some annoying i's because of signs. You have the contribution of just the function evaluated at the point, and there is a determinant due to the fact that around the point you have quadratic oscillations. Or the quadratic term comes at this order, basically. So I will explain what the various things are. So hf of x is the Hessian. The Hessian is the matrix of second derivatives, so it's this matrix. G is the metric, and this is a determinant, and then lambda is called, it has a fancy name related to Morse theory, the Morse index of the fixed point, but it's essentially the number of negative eigenvalues. Number of negative eigenvalues of g to the minus 1 hf. So essentially, if I have a negative eigenvalue, I'll get a negative sign under the square root, and it will bring out an I. So nothing fancy. So if you wish, this is the classical term. So this evaluates the classical action on the solution of the equations of motion. And these are the quadratic fluctuations, the harmonic oscillators around that classical solution. That's the physical interpretation here. Okay.
Sorry, can you repeat that last sentence? I didn't hear that.
I will repeat, just I want to finish this, that this is accurate up to this order, right? So, of course, this is not an exact answer, it's an approximation. It has the word approximation here. So I have extra terms suppressed by powers of t. So I was asked to repeat the statement. So by using this analogy between the function f and the action in quantum mechanics and the parameter t and the parameter h bar, I'm saying that this formula in physics would mean that you have solved the equations of motion, you have the solutions are xk, and at every solution of the equations of motion, the path integral receives a contribution, which is the classical action evaluated on the solution, which is this term here. And then something that knows about the quadratic fluctuation. So the partition function of the quadratic fluctuations around that classical solution. So harmonic oscillators around the fixed point. And that's the leading order answer. And then, of course, it's an infinite series in h bar in general. Was that clear?
Yes, thank you.
Thanks. Good. Okay. So far, this is hopefully not something that you hear for the first time, but maybe the next thing will be a little bit surprising. So take the following example. It's again mathematics. So I take the manifold to be the simplest odd, even dimensional manifold, S2. I put the round metric on the S2. Okay, these are the ranges of the coordinates. And I choose this function, f, cosine of theta. This is also called, if you know about Morse theory, this is called the height function. So if you imagine the sphere as, well, if you think of a sphere, there's the South Pole and the North Pole, and whatever my convention, this at the North Pole, this is -1, and then it changes. So this is theta equals pi, f equal -1, and f equal 1 here. Theta equals 0. That's the South Pole, and that's the North Pole. So it measures the height. So how far away are you from the, it's a monotonic function. Okay. So that's my choice, and I have to do my integral. This is not hard, but I'll be explicit just to emphasize a few points. Right, so square root of g is sine theta, and I'm integrating over the two coordinates. I'm really following up that prescription. And then this is an integral that even I can do, right? Nothing depends on phi, so this gives me 2 pi, and then you get d theta, let's say cosine theta, between -1 and 1. The signs are correct. And then you get 2 pi I over t minus e to the it plus e to the minus it, which is of course equal to 4 pi sine theta, sine t over t. All right. So of course I didn't have to write this intermediate formula, but I did to emphasize a point. So the function f of theta has two fixed points, 2 zeros. One is at theta equal to 0, and one is at theta equals to pi. So exactly at the North Pole and at the South Pole, the derivative vanishes. Okay? So according to this rule, I will have two terms. So if I'm imagining that I'm doing this WKB approximation or the stationary phase approximation, the leading term will be two terms at these 2 points, which is the value of the function at the point, e to the it, and then I have to compute this matrix and so on. So these two terms, this one and this one, are precisely those two terms there. With the 2 pi I t, everything is the same. Well, I didn't compute here the determinant of the Hessian. It's a 2 by 2 matrix. Yeah, anyway, that's not, it's very simple to show that these are two terms. But what happened here is the magical thing that there's no more terms. That's it. It's the full answer. So the stationary phase approximation is, and I cannot emphasize this enough, exact. Okay? This is some random, simple mathematical example that just is that. And you can say, okay, this is some accident because this is very simple, two-dimensional, very simple function. This cannot happen possibly in more complicated examples. But actually, not only it happens a lot. So there's some features here that can be generalized massively in mathematics. But the reason a physicist might care about this, if you know that such accidents happen in mathematics, and if you understand the reason behind them, you can then reasonably wonder, are there path integrals in physics where the WKB approximation is exact? Where I can exactly solve the path integral, not in some infinite expansion in some coupling H bar, quote unquote, but really that's it. So a classical term and then some fluctuations around it, one loop determinants in the language of quantum field theory. So that's really the interesting question for physics. And the answer is yes. You can do it in some cases. Okay, before we go to physics, I want to, well, make some comments on the mathematics here. So, comments. The first one is that the two terms, these two terms, this one and this one, correspond to the two stationary points. So that I already said, to the two fixed points or stationary points of the function. These points, these 2 points, are fixed points of the U1 action, or the circle action, generated by this transformation of phi. Okay? So choose a theta, choose a value of theta, this one, and you can go around the circle here, which is parameterized by phi. Okay? And so that generates a U1 group. So there is a U1 action on this manifold, which is very simple, this one. As you go to the North Pole, this U1 action degenerates. It has a fixed point, meaning that if I take a point here, somewhere that is not the North and the South Pole, it will be moved by this U1 action. But at the North and the South Pole, these 2 points are really not moved by the U1, so fixed points. Okay? And the third fact, which is, this is the non-obvious fact, this choice of f was nothing special. Any monotonic function f with, so f of theta only, so invariant under shifts of phi, that's important. And it has to have the same asymptotics, with the same asymptotics, I think up to order theta squared, at the 2 points, 0 and pi, will give you the same answer. So really, this type of integrals for any f of theta with these properties are computed by some simple formula, which is evaluating the integral and the integrand and the quadratic fluctuations around it at these 2 points. And this is a general statement. So in mathematics, there is a whole theory of equivariant localization, which is you take manifolds with some action of a group G, you study the action of the group, you find the fixed points, or more generally the fixed submanifolds, and then integrals of a specific kind on this manifold are going to reduce to a sum over the fixed points of the integrand and the quadratic fluctuations around it. So there's a general mathematical field of such things. Yeah. Right. So you do in this example, it will be a Taylor series expansion around these 2 points, and the function f of theta has to have the same. I should not call it f of theta. Maybe f tilde. The function f tilde is to have the same Taylor series up to quadratic terms with this function, but at the 2 points, right? If it's very easy to, I mean, there's not, it's kind of annoying to find an example. So I was trying last night, but it was after dinner, so I gave up. Yeah, I was not smart enough to, I wanted to illustrate with a specific example that you can go home and put on Mathematica, but I failed, so I will think about it again today. But yes. Yeah, but 1 plus what? Yeah. Yeah, but theta to the 4th will be good at one point, but will not be good at the other point. So you are making exactly the same mistake. So we're, yes. Anyway, we're only human. Don't worry. Yeah, so you see, this is one issue with mathematics I have. You prove something general, but then finding examples so it's a bit annoying sometimes. Anyway, yes. So there's this kind of important field of mathematics, and then once you know about this, you should ask, well, can I think of examples where the path integral in quantum field theory, which is an integral over not a finite dimensional manifold, it's not very well understood mathematically and so on, but still, can I imagine a situation where I can reduce the path integral to such a statement? Okay. Yes. Yes. The Hessian has to be the same. Yes. So the cubic terms can be different, but the quadratic have to be the same. Yes. I'm not sure where I was. Yeah. What is time? We have a bit of time. Yeah. So now I'll try to outline when such a thing works in quantum field theory. So obviously by what I've been talking about, it will work for some supersymmetric quantum field theories. You can already guess that. But broadly speaking, as one of you actually mentioned in their presentation yesterday, it's not really only true for supersymmetric theories. It works for other examples where in physics, in quantum field theory, we have a nilpotent charge. That's what you need. Something that is conserved and squares to 0. So, for instance, BRST, if you know what BRST is, the BRST charge is such a beast, and so you can apply these tools to non-supersymmetric quantum field theories that have some kind of a BRST structure. But anyway, so consider quantum field theory. So that's why I'm general with fermionic or Grassmann odd general Grassmann odd charge Q. So obviously, in a supersymmetric example, this will be the supercharge, but as I said, you can find it also in BRST. And then this Q, schematically, will square to a bosonic symmetry. So this is a very schematic equation. So for instance, in our example, that, you know, just to probably not confuse you, this one, sorry, Q1 plus, let's say, itself a squared vanishes, but two Qs that are not the same can generate a P, right? There was such a commutator, right? So this equation captures both of these situations. So this is some bosonic symmetry or charge. Okay? So obviously 0 is the trivial case, but the momentum is a non-trivial case. Okay, so now from now on I will be only talking about the SUSY context, just to be specific, and anyway this is the application that I'm going to study. So now consider the case of operators or states in the theory that are invariant under some of these charges Q. Or we call them short or semi-short. So BPS operator is another name for such a thing. There's many names. BPS operators, protected operators, short multiplets. Roughly speaking, these things mean the same. Something is being annihilated by a supercharge. So this operator, O, every operator here is called O in this class. So it's a horrible thing to call everything with the same letter, but yeah. So a schematic again, all of this is very abstract. So Q on O vanishes. At this point, I want to emphasize something kind of important. Nowhere am I using here a locality. So this operator O can be a local operator, like our phi and phi square and so on. But it can also be something like a Wilson line or something more exotic. Non-local operators, okay? Okay, so you may want to compute the expectation value of this observable. The two-point function of two O's, let's say, or something like that. Again, I'm being very schematic. Well, you have to integrate over all the field space, and you put an insertion of this operator, and so I'm going to be doing Euclidean quantum field theory. So this is the schematic thing that you have to do, right? This is this expectation value. And I've normalized, so in general here I have to put 1 over the path integral, but I'm ignoring such normalization factors, okay? Okay. So we may be interested in computing these. Now, before we do that, let's consider also another class of operators. So this equation is important. So the operator O is Q closed, if you adopt the language from differential geometry. But now consider operators that are Q exact. So again, using the fine tradition of horrible naming, I consider an expectation value of Q of some other operator O hat. So this is a Q, this operator, whatever you want to call it, omega, is a Q exact operator. So it's certainly Q closed because, you know, Q square is either a symmetry or is 0. Okay. So try to compute that. It's the same calculation. But now you should use, so I claim let me first write the answer and then okay. The answer is 0, I claim, but I have to explain a little bit. So Q, by assumption, is a conserved charge, which means that Q on S is equal to 0. The action of Q on S is equal to 0. So this is why I can move this bracket here. So this equation is true because Q on e to the minus S will give you 0. Is that clear? Okay. Now, at this point, in my head at least, I'm thinking of Q as a derivative, so I can use some kind of a Stokes theorem. Suppose that the measure, this mysterious object in quantum field theory, the measure in the path integral, is invariant under Q. This is an assumption. Q acting on d phi is equal to 0. Another way to say this, for those of you who know anomalies, is when I have a symmetry and the measure is not invariant under the symmetry, this leads to quantum anomalies. So I'm assuming that there's no quantum anomaly for the charge Q. There's no SUSY anomaly. The other thing I'm assuming, so this, if there's no SUSY anomaly, this will allow me to put Q outside of the integral, roughly speaking, to integrate by parts. And then the final thing I'm assuming is that this object decays fast enough in field space. I'm doing an integral over field space, so I'm assuming that for large values of the fields, this is somehow suppressed. So falls off fast enough. So the integrand decays fast enough. And yeah, I'm not specifying what this actually means. All of this is very, very schematic. Okay, so in such a situation, I have that all of these correlators vanish. Good. So, if you're sufficiently mathematically oriented, and I've already used the language, so you could have a hint of what's going to happen. Oh, crap. Anyway, let me just finish one word and then I'll stop. So you can quickly arrive at the notion of cohomology in field space. What do I mean by this? Well, the expectation value of this observable OBPS is the same when you add any Q-exact operator. Right? So I have a class of observables that give me the same answer. So I can mod out by this. So cohomology, you look at the kernel, we look at the image, you mod out whatever the image by the kernel, and those are the juicy things, right? And so here I can mod out by such operators. And this will be the start of arriving at the SUSY localization formula. Good, I'm going to stop here because you need a break and there's Chris after me, so yes, thanks.